Now let's move to solve for resistance. Resistance in a rigid tube can be set up by this particular equation. Here we're going to use 8 times the viscosity times the length divided by pi r raised to the 4th power. What you really need to think about in this equation is what items can be changed in the cardiovascular system. First, you will be able to alter the viscosity of the fluid if you're dehydrated versus hyperhydrated. The length of each individual tube should be fairly constant because once a blood vessel has been developed and you have an adult, that blood vessel length is not going to change. But what do you have the ability to change from on a minute by minute or even second by second basis? That is the radius of the tube. And since it's raised to the 4th power, the radius becomes incredibly important. If you go from a tube that is only this size to a tube that is this size, that increase in radial diameter of the tube allows for greater amounts of flow. And that's simply because there's less resistance to the delta P. What other changes happen in terms of flow? In terms of flow, we need to think about 2 different types of flow. The equation that we just saw about resistance is only related to laminar flow. And what do we mean by laminar flow? Laminar flow is the flow in which there is no turbulence or turning over of the various fluids. In this type of a graph where we plot flow over a change in pressure, laminar flow can be seen as this straight line. Turbulent flow happens if there's too much pressure for any given tube, or if there's some sort of occlusion in that particular tube. The other problem with turbulent flow is that you lose energy. It is less efficient to move fluid through in a non-laminar means. And therefore, you really want to think about if there are areas of turbulence in a blood vessel, these have to be accounted for because they are going to change the resistance component through that tube. And why would this happen? If you've done something like decrease the luminal diameter of the tube, you've changed the resistance and possibly now even the type of flow through that tube. This is showing you an example of laminar flow. This is this kind of projection of fluid. You notice in laminar flow, there is the fastest flow in the center of the tube. That is because there's the least resistance in the center of the tube compared to the 2 edges. The 2 edges provide the resistance which slows down the fluid. Turbulence is heard through a stethoscope in a couple of different manners. The one is through a murmur, such as a valve. If you're going through a valve and there's turbulence at that valve, you can put a stethoscope over that valve of the heart and listen to it, and you hear a murmur. You can also hear a Brit, and this occurs at a blood vessel, and this is related to this atherosclerotic lesion that might take place, and you can hear the turbulence just after the lesion. Good examples of this are in the carotid arteries here, also in the femoral arteries if you have these atherosclerotic lesions.